Hello everyone and welcome back to the Cisco Optics Podcast, where we talk about pluggable optics for networks. Manufacturing of optics has been historically cumbersome compared to electronics. With optics, you have to align components and glue them down or laser weld them. It was often done by hand because there wasn't enough volume to justify developing fancy robots. Compare this with electronics, where you put tons of devices on a single wafer and stamp them out in a highly automated fab. After years of effort, we finally have a way to stamp out optics too. It's called silicon photonics. The beauty is that we didn't have to reinvent the wheel. It leverages the existing CMOS infrastructure that was already there. This is episode 17, and we continue a conversation with Ron Horan. Ron joined Cisco through the Luxtera acquisition in 2019. Luxtera was spun out of Caltech by a group of professors and students and was known for its groundbreaking approach to silicon photonics. In this episode, we continue with the benefits of silicon photonics. Ron attended the University of Texas at San Antonio for both his bachelor's and master's degrees. His master's thesis topic, entitled Synthetic Vision Landing Aid System, was patented as a first GPS-based aircraft landing aid. From 1994 to 1999, while at Compaq, he earned 15 patent awards. In 2001, he joined Broadcom Corporation, where he managed field applications engineering for the compute segment team, ran program management in the networking BU, and was a senior director of sales and strategic account manager covering the Hewlett-Packard worldwide account. In 2011, Ron moved to Luxtera, where he worked as vice president of sales before moving into the role as vice president of marketing. Luxtera was eventually acquired by Cisco in 2019, where Ron now runs product management for the Cisco Client Optics Group. What an impressive journey from a technical focus to business leadership roles. If you haven't already, please subscribe to this podcast. On Apple Podcast, you would follow us now. Depending on which platform you use, we may be part of the Cisco Podcast Network. Check out our blog at blogs.cisco.com and search on hashtag Cisco Optics Blog. All one word, no hyphen, and no spaces. You'll find podcast notes and links there too. For our YouTube playlist, go to youtube.com and search on Cisco Optics. And for product information, go to cisco.com/go/optics. And now, join me as I talk with Ron Horan.
You were asking the original question about why silicon photonics, right? I think what started this long.
That's where I was going with it, yeah.
Right. So the benefit of silicon photonics, at least to us, is that number one, it's an electronics process. It's a standard cell CMOS process. So if you compare like a traditional optics, you've got a bunch of like I said, the bag of parts. Whereas what you're doing with silicon photonics is you're manufacturing a wafer at a fab like TSMC, and that basically has the optics transceivers on the wafer. And so instead of assembling a bunch of piece parts, now you've got it's all in a die, right? And the thing about that is now all of the best practices of the semiconductor industry, process, meaning, minimizing process variation, repeatability, testability, reliability, all the different, the best practices of the semiconductor industry come to bear on this photonics wafer. And so, and you have, it's when you couple a photonics or an electronics die on top of the photonics die, and you add your light source, you basically have, an entire, 400 gig transceiver that's smaller than your fingernail, and that's it. It's all in in that package. And so if you compare just that process, which is a very refined process where it's all parametrically driven. Before you've ever diced the wafer, which sites on that wafer are good transceivers and which are bad transceivers.
And what do you mean by parametrically driven?
Well, just like any silicon process, right? You're basically building a device based on certain parametrics, right? In other words, in order for it to be a good device, you have to ensure that hundreds, if not thousands, of parameters are met. And the only way you can possibly do that is through like a standard cell CMOS process. And the way you test that is you bring the bed of nails down on top of it, and you could test each transceiver individually before you've ever diced the wafer. And you know every single parameter that is required to be met before you ever dice the wafer is within specification. So going back to what I was talking about.
So you don't have to go through the trouble of building a whole module in order to test it, only to find out that you have to throw away the entire module.
Right, exactly. Right. Whereas, before I've ever diced the wafer, I know if that P die is a good P die. So I don't go put an E die on a bad P die. I don't put a light source on a bad P die. I don't put that into a module. So I'm actually taking my yield hit as I go. The other thing is the yields are significantly higher. I mean, yields for, the P die, and the E die, obviously, and the light source, those are in the high, numbers, very high numbers. And
is that because you've taken human labor out of the process?
You're taking human labor out of it, but it's just a more refined, known process. So in other words, it's much more controlled. And so consequently you get, what you get out of that is you get extremely high yields. That's not the only thing. It translates to, like I said, reliability. It translates to repeatability.
How is it more reliable?
Well, because, optics, the problem is, again, if you assemble a bag of parts and you put them together, they tend to have more issues with infant mortality. So, historically, that's always been the knock on like a DML is that they're just, the failure rate is all over the place. Fit rates are high. Whereas
and these failures are things like maybe the epoxy isn't cured right or something like that.
Well, I think again it comes back to taking a set of individual components, sticking them together, and they all have their own, one may be on the high end of its specification, another may be on the low end of the specification. If temperature affects that. So historically, more traditional optics have been deemed as not as reliable. That's why people tend to prefer copper over fiber, just because of the reliability. But silicon photonics is changing that paradigm, right? And so because every parameter before you ever ship the product, exactly where that product's going to fall. First of all, it's not a bunch of piece parts. It's literally all combined.
So with the piece parts, each piece part has been fabricated under its own process, whereas with the E die and the P die within the wafer, every single component of the E die or the P die was made with literally the same process, right?
Exactly, and it's in a tightly coupled set of parameters. If it's not, we don't use it, right? So, that's why you run DVT and qualification on products, is to ensure that, that over temperature, voltage, different things like temperature, voltage, that that this product is going to stay within the standard. It's going to stay within the margins, that range that it's supposed to, and then you add margin on top of that, right? So that it could get hit with the minus 40 degrees C and high voltage or low voltage, and it's still going to function. So I can't emphasize enough how important that is, because again, our fit rates, we've been told by customers that our fit rates are an order of magnitude better than anybody they've ever seen before. And there's also just the scale, right? We talked about the die per wafer. I mean, if, TSMC or Global Foundry, they can pump out wafers, all day long, and if I'm getting, just a random number, if I'm getting 1,000 transceivers per wafer, then it doesn't, I can literally build millions of units, relatively quickly. So the scale of it you can scale out very easily, depending on your demand. And, it's not that difficult.
The scalability you get with those from those fabs, it's already there, right? Because they've already invested. There's already been an ROI based on other industries like wireless, iPhone kind of stuff.
Yeah, and the great thing.
So we're basically piggybacking off of that, right?
Yeah, and the great thing about Luxtera Silicon Photonics is basically we use standard CMOS processes. So we have our own design library that we've created. It's at TSMC, for example. We have our own standard cell CMOS processes. So you're not doing exotic. You're not having to do exotic. It's them processing a wafer just like they would, a controller chip for an iPhone. It's no different. So, and again, that's one of the benefits is just the sheer scale of being able to mass produce transceivers. So
it's highly leveraging that investment from other industries, right?
Absolutely, yeah.
Because our industry didn't have the volume to justify what those fabs had to build.
Yeah, that's absolutely correct. So, and then the other thing here is, and we've touched upon this, is that everything, if you look at our manufacturing process, it's almost entirely fully automated. I mean, instead of a bunch of people in a room, somewhere hand assembling modules, it's fully automated. And so the only, human interaction is just loading things into machines, right? And just turning the machines on and making sure that, that nothing's going wrong, but you're not, it's all done with automation, which again adds to, goes back to reliability and repeatability and just, scale again. And so,
and even that automation infrastructure is already there, right? For the CMOS industry?
Well, it's some of it's there. Yes. Some of it's there for the some of it's there for the silicon manufacturing itself, but the assembly part, the module assembly, for example, to do a fiber attach, we have an automated machine that does that, right? And it just can pump out. It can put fiber onto the machine, onto the P die, it's one after the other repeatably, and gets the fiber array in the optimal location every single time. And the yields are super high on that. And so, again, going back to the old way of doing things versus the new way of doing things, it's just much more, it just makes more sense, right? To do it this way. It's funny, if you go back and you look around the 2013.
That was the third part of my conversation with Ron Horan. Next time, we'll get into the industry's response to silicon photonics. Subscribe to this podcast, and we'd really appreciate you helping to get the word out. Share this with friends and colleagues that come to mind when you think of network technology and optics. And leave a review on Apple Podcast. We're also on all the other major podcast platforms. You may see the Cisco Podcast Network come up when you search for Cisco Optics Podcast. That's where we live, and you can find other great podcasts there too. Also, check out the Cisco Optics blog at blogs.cisco.com and search on hashtag Cisco Optics blog, no spaces and no hyphens. We also have educational videos on YouTube. Just go to youtube.com and search on Cisco Optics. Thank you for listening. This is Pat Chow, Product Manager at Cisco Optics. The next episode is part 4 of my conversation with Ron Horan. Until next time.